Okay, so this is just stuff for next class. A lot of what we're doing today is going to set you up really well for bootstrapping and confidence intervals. And so, yeah, midterm was due yesterday. Yep. Okay. Okay. My class, we're going to talk about statistical inference. So this is where the class starts to get really fun because we're out of the land of like descriptive statistics and into inferential statistics. This is my cat. That's him when he was a kitten, and that's him yesterday. Yeah, and his name is Mr. Avalo. And he has a bat costume for Halloween, so I'm really excited about that. Okay. So the basics of statistical inference is basically we have this entire population, and there's some mean or proportion or something that we're trying to estimate, right? But we can never actually collect data about every single person. So we have to select some people from that population and use that sample to calculate our mean or proportion to approximate the population. So that's really the basis of like everything in statistical inference is we are using information from a sample to make conclusions about an overall population. General terms, parameters are just anything to do with the population. One thing about it is like, we're never going to actually know what it is. I mean, there's maybe some cases where you can measure something from every single person in a population, but not really. Like, that's not realistic. If we think about like the entire US population, there's no way we can take data from everyone. So we have some numerical value and we don't know what it is. Almost never. The statistic is what comes from our sample. So that is measurable. And that's the numerical value where it's like, we know it, it's called a point estimate of that population of the parameter. And then we can use it to basically see if we think something is true about the population, how likely is it that we get this point estimate? Like I said before, parameters are fixed values, so they're never going to change. We don't know what they are. However, the statistics, so depending on who we select as a part of our sample, our point estimates will change, right? Because it's just based on the people we select in our sample. So that's kind of like a fundamental idea that a lot of people, it seems obvious, but a lot of people forget it, where basically we have like this unknown value that's always going to be the same. And then we have our sample value, which will change depending on who's in our sample. Does that make sense? Yeah, okay. Okay. Sampling variability is basically the differences between our samples, right? Because depending on who we choose, it's different. So we have some variability between if we took like 10 samples, they're all going to be a little different. Now, sometimes if we have like a ton of people, so think about things like census data where we collect just all this information, we can create multiple samples. However, we normally can't do that. Normally, we're just working with a single sample. So a lot of the statistics that we're going to talk about and things that are computational, so bootstrapping, which you all will do for your next data tutorial, and then permutation and randomization, are based on this kind of assumption that our sampling is done at random. So just keep that in mind when you're thinking about kind of an underlying population distribution of sample point estimates. We're assuming that those samples were selected at random. Now we're going to do an example that I'm really excited about. So let's put this up. And what I'm going to have you all do is I made cookies, and I want everyone to take 2 cookies. And these are awesome. And we're going to model the population distribution. Okay, so each cookie here is a sample. Let's pretend this is not true. Let's pretend I bought just like a ton of chocolate chips, like thousands of chocolate chips. And there was like a mistake at the factory and some ended up being butterscotch. So what I want to do is I want to look at the population, like I want to try to estimate the population parameter based on my samples of cookies for my like overall thousands of chocolate chips, where each has a probability of being either butterscotch or chocolate. Okay, so binary outcome. So the first thing I'm gonna do is figure out for my sample, this one has 1, 2, 3, 4, 5, 6. So every single sample size is 10. And this one has 1, 2, 3, 4, 5, 6, 7. Okay. This one has 7 chocolate chips and 3 butterscotch. So if I make a graph of just this sample, I can say 0 and 1. Let's say 1 is chocolate chip and 0 is butterscotch. I have 7 here and 3 here. This is not normal, right? There's no way for this to ever be normal because this is just my sample distribution of a binary outcome. However, if we take each sample and we plot it, so we plot all of our sample proportions, it's going to be a normal distribution. And we're going to do that here, okay? So we're going to see how this goes. So my first one, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to calculate the proportion for each of these because it's out of 10. This is just going to be 0, 1, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 10. Okay. So I had 7. So I'm going to add 1 here. Okay. Do you want to tell me the proportion of yours?
Yes. So for one cookie, it is, let me see, 1, 2, 4 chocolate.
4.
And 5 butterscotch for cookie.
Okay. Do you want to tell me your proportions?
Yeah, so one cookie has 7 chocolate and 3 butterscotch. And the other one has 5 chocolate and 6 butterscotch.
Okay, let's pretend. So yeah, okay, let's do that. So 5 butterscotch and 6 chocolate. The proportion
Other
is
way around, 6 butterscotch.
6 butterscotch, 5 chocolate.
Mhm.
So it's a little less than 0.5, so it'll be like here. Right, ish. Okay,
Do you want one cookie?
whatever works. Yeah.
I have 3 chocolate chip.
Okay.
And 7 butterscotch.
3 chocolate chip,
And the other one I have 3 chocolate chip as well.
3 chocolate chip. Okay,
So I said?
yeah.
3 chocolate chip and 5 butterscotch for the first one. And then the second one is got 4 chocolate chips and 6 butterscotch.
Okay. Nikki.
One has 5 chocolate and 5 butterscotch, and the other one has.
Okay.
One has 5 chocolate chips, and the other one has 6 chocolate chips.
Okay.
One has, 6 chocolate chips, 4 butterscotch. One is the same.
Same.
But no, the other one has 5 butterscotch.
Okay.
and chip.
So you're just plotting the chocolate chips?
Yes, so this is just proportion of chocolate chip because it's
Oh.
binary, so it'll be the same.
Oh, I do have based on like Sarah's sampling, I do have like a missing chocolate chip on another,
Okay.
so it's actually proportional, 5 chocolate and 5 butterscotch.
Perfect, okay. So yeah, so then we'll just add that here. And then mine has, or I'll do mine. 6. 4. Morning. Good morning. So Sarah just went, yeah. Okay. Do you guys notice anything about this? Looking a little normal? Okay. Okay. Sarah, do you want to go?
I have 4 and 4.
4 and 4. Okay. Okay.
I have 3 and 6.
3 and 6. Whoa, look at this. It's a normal distribution, right? So when we take a ton of samples, even if the underlying distribution itself is binary, which is not normal, the means, or in this case proportions, of all of our samples will approximate a normal distribution. Does that make sense? Okay, now you can eat your cookies. Yes.
With this,
Oh, so this is just we're pretending this is just simple random sampling where I just took everything and just like threw them all out onto the cookies. Yeah. So if we want a better example of this, where it's like official in real samples, we can use something that Brad sent over. So basically this is from StatCrunch. So let's say we have a population. Oh, I'm not sharing anything. I'm sorry. Yeah.
Slide.
Okay, I'll add them in. Thanks. So if we run a sample one time with the sample size of 2, we end up with these just like, 2 people. It's not going to be super accurate. Our mean that we get for them is 30, which is like not too bad. But if we run another, like it can just be so many different things. That's that sampling variability that gets into there. However, if we run it 1,000 times, we get a normal distribution, right? The means of all of those samples make a normal distribution. Cool? Yeah. And the center of that sample distribution will be our population parameter. So this is the foundation of like everything that we're going to talk about. So things like p-values, confidence intervals. It's based on this idea that if we just ran a ton of different samples, it's going to be a normal distribution. And the center of that normal distribution will be our population parameter, the true population parameter that we never actually truly know. Does that make sense? So basically, like we talked about before, anything in stats is us using sample data to test a claim about the entire population. In order to do that, we have to have claims to test to begin with. So there's 2 that you will make for any question that you get. There's 2 hypotheses that you should write. The first is going to be the null hypothesis, which is actually what we're testing itself, is the null hypothesis. And it is basically the idea that there is no difference between either separate populations or a population and a null value. And then our alternative hypothesis is that there is some difference between things. So normally when like when people use the word hypothesis, like if researchers are like, we hypothesize that this thing is going to happen, what they're really talking about is the alternative hypothesis here. So if we like think something is going to happen, that's our alternative hypothesis. Our null is just the opposite of that. So that's kind of an easy way to remember it, is like when whatever we think is going to happen normally is going to be our alternative hypothesis. So let's do an example, because I think it's confusing when we think about it in terms of no difference. So let's say that there's a physical therapy group and they're looking at whether there's a difference in reaction time among high school athletes compared to the general population of high schoolers. So the first thing that I would do is I'm going to say, okay, what is the population parameter that I'm looking at? In this case, it's going to be a mean, right? Because it's mean reaction time. And it's written as mu. We'll get into kind of the notation in a little bit. But mu, we are comparing to the null value, a value of 592 milliseconds, and then direction of it. Okay, so that's what's hard, is I think a lot of people, when they think about a null hypothesis, they think about it being like mu is equal to mu. That's not always the case, because in this instance, what we think is going to happen is that student athletes are going to perform better than the general population. So it's not just that we think that they're not equal, it's that we think that it's better. So our null hypothesis is going to be that the mean reaction time among athletes is greater than or equal to 592. Does that make sense? Okay, our alternative is just the opposite. So what we think is going to happen, mean reaction time is less than 592. Okay, does that make sense? Yeah. Okay, now we have a different one, and this is just to show that one, it can be different in terms of directionality, but also it can be a different population parameter that we're trying to estimate. So in this case, it's testing how an end of life like discussion influences whether people choose to go into hospice. So choosing to go into hospice, people either choose to go into it or they don't. So it's a binary outcome. Our population parameter is going to be a proportion. And we're comparing whether group 1 who got the discussion is different than group 2. And it says specifically, they don't know if this conversation leads to more or less hospice election. So we don't know the directionality of it. So this is a case where our null hypothesis is just that they are equal to each other. Does that make sense? Yes.
So, okay, like the previous question, so alternative would be the one that we expect and no is like.
Yes, exactly. Yes. The only one tiny caveat to that, to it always being that like your alternative is what you are thinking is going to happen, is like sometimes researchers will go into something thinking that there's going to be no difference between things. And if that's the case, the null hypothesis still has to be that there's no difference between them. Does that make sense? And you're never actually going to like be able to test that. Just ignore that. It's just like a small caveat that like sometimes we might expect the null to be the truth, but the way that we do hypothesis testing is always that the null has to be that there's no difference between things. Okay, or it's no different or less than or greater than. So in this case, we're just testing whether the proportion in group 1 is different than the proportion in group 2. So our null is that they are equal to each other. And we just say the proportion is the same between groups. And then our alternative is that they are different. We don't necessarily know which one is going to be a higher proportion versus a lower proportion. It's just that they're different. Does that make sense? Okay. So one thing that I think is important to keep in mind too, and we'll go through kind of the steps of developing hypotheses, is that when we think about a null hypothesis or alternative hypothesis, it's all about what's actually going on in the population. So we talked about how before with population parameters, we never actually truly know what it is, right? But our hypotheses are saying, basically, this thing is true in the population. So our null hypothesis is for our total population, there's no difference. And then we test that claim based on the results from our sample. Does that make sense? A little bit? Okay. So there are my cookies. I don't know why I put them there, but you're welcome. I'm just kidding. So another thing that we talked about before is the directionality of it. And with the directionality, we need to make sure that the entire probability space is covered. And that's just a really confusing way of saying, make sure that your null hypothesis and alternative hypothesis align with each other, right? So if we're saying that the two population parameters are equal to each other in our null hypothesis, our alternative is that they are not equal to each other. So we wouldn't say that one is greater than the other for our alternative hypothesis, or that they're equal to each other for our null hypothesis. Got it? Everything has to be included in our hypotheses in some way. Okay. So there's 3 things to do when you're writing hypotheses. First is figure out the parameter. Second is the direction. And the third is the value of the hypothesized parameter. And we're going to go into these in more depth soon. Okay, so parameters and what's important to know about them. Basically, we can test kind of anything in a hypothesis. Any kind of point estimate that we would get from a sample, we can test. So that can be a mean, that can be a difference between means, that can be 3 means, that can be 1 proportion, 2 proportions, that can be risk ratios, slopes. Just remember, it's all in the population. So when we write hypotheses, it's population values. So what I would remember or write down on your note sheet is, or just know that mu is a population mean, okay? Sigma is a population standard deviation. And then proportion, we just use P. Those are the big ones. We've talked about beta a little bit. So this is slopes. So it can be beta, it can be beta not. Correlation coefficients are rho. I think that's rho. I don't know. Those are the big ones. I would really remember sigma and mu. And then also we've talked about slopes, so you should know beta at this point too. Cool. Okay, and I'll upload these slides. So the second thing after we identify what population parameter we're working with is to figure out the direction. So we talked about kind of equal to versus greater than, less than, so on. We denote these with kind of two-tailed, right-tailed, and left-tailed. So remember how last class we talked about a normal distribution, how you have tails of it that you're testing the probability in? That's kind of what we're doing when we think about null hypotheses. So different from not equal to as our alternative hypothesis is a two-tailed test because we can test the difference can be on either side of the tail, right? When we think about that population distribution. Right-tailed is just going to be greater than or more than because that's on the right side. And left-tailed is less than or fewer than. Does that make sense? Yes. This is, yeah, these are the alternative hypotheses. Yep.
So when you're saying right scale means the alternative hypothesis would be greater than.
Yes,
the value.
exactly. Yeah.
And if it's left scale, means the alternative would be less than them.
Exactly. Yes. Yeah. And so our null hypothesis for the first one would be equal to, this would be less than or equal to, and this would be greater than or equal to. Cool. And then the third part is we need a null value. So let's raise this. So a null value is basically the value that you're comparing to whatever population parameter. So if we have a single mean, mu A. If we're comparing it to something, it's like that student athlete example, right? We need to have a value that we're saying, hey, it's equal to this value. It's less than or equal to this value. So it'd be mu A, let's say less than or equal to 500. This here is our null value that we're comparing against. And we have to always have some null value. Now you might say, wait, we also said that it could be like mu A is equal to mu B. Like there's no null value there. Those are both population parameters. The key here is that our null value is 0 because this is the same as mu A minus mu B equals 0. Because the actual kind of population parameter that we're working with is a mean difference. We're saying that mean difference is not equal to 0 for our alternative, or is equal to 0 for our null. That makes sense? Normally our null value is 0 because we're thinking about like, is there a difference? For betas, right? For like slopes, maybe we're testing whether there is, it's equal to 0. If you look on kind of the SAS output, that's what it's testing against when you see that p-value. Yeah, not always 0. If we're given what the value is in a different population that we're comparing against, it's that value, but we normally think about it in terms of being 0. Questions? Mu, so mu is just the population mean. So mu just is mean, sigma, standard deviation, and p is proportion, but in the population. So if you want this population, how do you know mu? Yeah, you never know mu. So when we write out hypotheses, we are basically saying we have no idea what these actually are, but our hypothesis is that mu is less than or equal to 500. But like that's kind of the thing with it being a population parameter is we'll never actually know what mu is. So what's 500? 500, so this would be like in the example of student athletes, we were given a value. So you'd be given a value in a question. It would be like the population, we want to figure out for, there's some guideline that says a certain medication has to be some % of the actual medication on the label. So if it's like, if we have P, it has to be greater than 80% of the value. Our null hypothesis might be that it's less than. So we're given like, we want to test whether it's different than this value. So this is just called our null value. That makes sense? Okay. This is just some basics of everything. Let me pull this down again. So hypotheses can involve anything like we talked about before. I think that was close. This is just an example where it's one mean. So if it's one mean, like we just talked about, we have to have a null value here and it's given to us. We would never like just guess what it is. We would have to have some justification. So our null value might be 0, it might be 500. If we're testing one mean, we just have it equal to that yeah, is it just different? If it's greater than, then our null hypothesis that it's less than or equal to. And then less than our null hypothesis greater than or equal to. Make sense? Okay. We can also do it with two means. Key here is to remember that our null value is 0 because we're taking the difference between them. So you can write it out either way. You can write it out as like mean 1 is equal to mean 2, mu2, population. Or you can do the difference between them. I prefer to do the difference between them because what we're really testing is, you know, a mean difference being different than 0. But you can do either way. Any questions? All right. Now we're going to work on a worksheet and then we're done for the day. First, I'm just going to go through an example of what we need to do in the worksheet. So I think this is from the data tutorial. It was like people were either given a file with a male or female person on it. Other than that, they were exactly the same. And is there a difference between promotions? So what we're going to do in the worksheet is we're going to write out the population parameter and then write out the hypotheses. So if I'm reading this, I'm saying, okay, so we're giving bank supervisors personal files and they're asked whether the person should be promoted, yes, no. So what is the outcome? Binary, right? So it's going to be a proportion. To branch manager, they were identical. Half of them were male and half were female. So I know I'm working with two proportions, one male, one female. And there's interest in whether the promotion decision depended on gender. We're not given any direction. So we're just testing whether or not they're different. So our population parameter is proportion. And we have two. We have proportion male and proportion female. Our null hypothesis is that they're equal to each other or their difference is equal to 0. And then our alternative is that they are not equal or their difference between them is not equal to 0. The reason why is we don't specify direction of it. Does that make sense? Okay, I'll leave this up on the board and I'm going to hand out the worksheets to do, and then that is Okay, hi everyone. So the video cut off a little when we got to the questions. So I'm gonna just go through them here and hopefully we can go through it in simple terms. I've highlighted some things in the question just so I don't have to read them out loud. But hopefully this will help clear any questions that you have up, and if not, feel free to reach out to me. So the first one is asking about arsenic-based chicken additives. And it's asking if it's greater than 80 parts per billion, right? So when we think about parts per billion, we're thinking about a level of something. That tells me that the population parameter that I'm working with is going to be a mean, right? And we're given that it's an average in this case as well, and I can highlight that too. That might make it easier. So we're told that we're looking at the average. So for specifying what my population parameter is, I know that I use mu to represent my population mean. And I'm going to say mu is arsenic level in chickens for any given supplier, right? Let's say, for a supplier. And we're not given, you know, specific suppliers. We're not told that we're comparing different suppliers. We're just saying if this arsenic level is greater than 80 parts per billion in a supplier, that's when it's not going to be released, or it's going to be a concern, right? So we really only have one mean that we're working with here and one null value, right? So when we write out our null, we know that it's greater than 80 parts per billion. So if it's greater than 80 parts per billion is kind of the thing that we think is going to happen. That's going to be our alternative hypothesis. So it's going to be that mu is greater than 80. And our null is then going to be the opposite of that, right? It's less than or equal to 80 parts per billion. We know that because we're given greater than 80 parts per billion. Our null is that there's kind of no difference, and then our alternative is generally kind of what we're actually
suspecting is going to happen. Okay. Scenario 2, we're given brand A and brand B, which is tricky because you might think that this is two groups, but it's not. We'll get into that in a second. And we want to look at the proportion of people that prefer brand A. So we know that we're looking at the population proportion, right? I'm just going to write P. And here's the thing. So when we think about proportions, in this case, it's a binary variable, right? They can either choose brand A or they can choose brand B. We are not comparing the proportion between the two groups. We're only looking at one overall group and then the choice of what they choose, right? So what our hypotheses should be getting at is not whether there's a difference between the two brands, because we know that they're basically the same thing, right? So like if we have a proportion of A, that's just equal to 1 minus the proportion of B. We're looking at whether the proportion of A is higher than, right, the likelihood would be, or higher than the proportion would be if everything was just 50-50. So because of that, what we're really comparing to is 0.5, right? We have one group, we're not comparing between two groups, we're just looking at whether the proportion of A is different than 0.5, or in this case, greater than 0.5. So our null is gonna have to be that it's less than or equal to, so this would be people either prefer brand B to brand A, or it's the same between them. 0.5 is our null. And our alternative is that P of A is greater than 0.5. And so that's where it gets a little tricky, because I saw a lot of people kind of trying to compare the two proportions. And it's not that we're doing that, right? We are just seeing whether it's different than chance, okay? I hope that makes sense. Feel free to reach out if you have any questions. Again, I guess I didn't do this here, but we would want to specify what our population parameter is. So we would just say PA is the proportion of people in the population who prefer brand A. Okay. Scenario 3, it gets a little easier in terms of like the simplicity of it, but instead of working with proportions and means, we're working with median. So we know that that's our population parameter, but in this case, we're comparing two groups. We're comparing Hispanic patients and non-Hispanic patients. So there are two groups that we're comparing the medians of. So we're gonna say median of H is equal to the median time on ventilator for Hispanic patients in the overall population, and median of non-Hispanic is just equal to that median time on ventilators for non-Hispanic patients. Okay. When we get into making our null hypothesis, we're not given a direction here. We're just looking at whether there's any difference at all. So because we're not specifically given a direction, our null is just going to be that they're equal to each other. And our alternative is going to be that they are different than each other. And we represent difference by just having our equal sign and crossing it out. And then that's all you have to do. So not only can we do it with medians, there's some other, statistics, or I guess, different types of numbers that can come from what we are trying to estimate in our population. And in this case, we're thinking about a linear relationship. So what's a measure of linear relationship? Well, one of the only things we've really talked about is a correlation coefficient. So I'm going to use rho to represent this, which is kind of like a P, but it's not a P. So I'm just going to say this rho is the correlation coefficient in my population between household income and children under the age of 18. Easy enough, right? So this is the same thing as before, we're setting up all of these hypotheses in a pretty similar way, because our null and alternative will still be kind of that equality and then that non-equality. However, we can do it with any type of, number that's a measure of something, right? So when it's something linear, well, it's when our correlation coefficient is, positive or negative. And so we want to test in this case whether it's, again, different from 0. So our null is just going to be that row is equal to 0. And our alternative is that it's not equal to 0. It can be either positive or negative. Okay, last one, and this is where it starts to get tricky because I think this scenario 5 question is set up in a different way than the scenario 1 question, but has a similar answer. So let's take this a little bit slowly. So we are asked, basically, let's pretend that we're the FDA, and we basically, in order for any drug, or in this case, we're given a generic version of a drug, it needs to pass a certain threshold of a key metabolite, like in relation to something else. So in this case, we're told that we have a new kind of branded medication, a new generic medication, and we need to make sure that it is no greater than 110% of the level of the same metabolite from a branded drug. Okay, so let's start out easy. What's our population parameter? Well, we know that it's just a level of something, right? So let's, in this case, I'm going to talk about mu, but level, that could be a median. Normally we do work with just means though. So I'm going to say mu, which is the level. Ooh, yikes. Ooh. I have one shot at this, so I'm not starting over. Level of the metabolite in generic med. And we do have to specify here that this is mu g, because we're gonna have 2 means. And then we have a second one that's the branded drug. So we are kind of comparing 2 groups here. Then we have mu b, which is level, and both of these are mean, of metabolite in branded drug. Okay? So here's where it gets tricky. So we need to figure out how mu g is related to mu b in our hypothesis. And we're told that it's 110% the level of a metabolite. Okay? So what's going to happen? Well, we're going to have to multiply mu b times that value, 1.10. So this is 110% of that level. So now we're going to figure out the direction of it, and this is also tricky. So we're given here that we're looking at whether the key metabolite is no greater than 110%, okay? What does no greater than tell us? No greater than tells us that it could be equal to it, right? So it's going to be mu of g is less than or equal to, right? Because it's not necessarily that it has to be less than, it's that it can be less than or equal to. It's no greater than 1.10 times mu b, okay? We can set this up also as, if we divide both sides by mu b, then we get mu g over mu b is less than or equal to 1.10. And so in this case, I like this setup because then we get our null value here. I didn't mention this on the front side, but in this case down here, when we're doing these medians, because we have 2 groups, our null value is 0 because we can subtract from both sides, and we have median h minus median nh is equal to 0. 0 is our null value, and then it would be the same for our alternative, except not equal to 0. So I'm just setting up the same thing here. Either of these answers are appropriate, but we just have to set it up that way. Okay, so I set this up, and it's easy to think, okay, well, what these researchers think is going to happen, or like what they're actually testing is whether it's no greater than 110%. However, when we look at these equations down here, or these set up for our hypothesis, what do we see? Well, we see that there is an equality statement here, right? So it's not just less than, it's less than or equal to. We know that when we set up null hypotheses, they have to include that equality statement. We don't have alternative hypotheses with that. So therefore, this is going to have to be our null hypothesis, okay? And the reason why is because we're told no greater than here, which includes anything less than or equal to that. For our alternative hypothesis, it's just pretty straightforward because it's the opposite of that, right? So it's going to be mu G over mu B is greater than 1.10. Okay, so the reason why is because this includes that equals, okay? So, you know, one thing that we think about when we set up null hypothesis, and this is hypotheses, and this is more from kind of a, you know, like a logistical standpoint of like, what is the FDA really testing? Well, when we set them up, our null hypothesis, so H naught, is kind of like what the status quo is, right? So we kind of go into this test assuming that there is safety, right? And then we're providing evidence either for or against that. And so that's why in this case, our null hypothesis is kind of this less than or equal to thing here. It's the same as before when we had the chicken example, even though in this case we're given is greater than 80 parts per billion. In this case we're given is not greater than, so no greater than, but it's still our null hypothesis down here that includes the kind of less than this safe level of something. I think that that's, you know, an important idea behind what we're trying to do with a null hypothesis. But I think the key is just really to read the equation, or sorry, read the question, set up kind of, hey, what are we trying to test? So something like this, and pay attention to really what this relationship is. Is it less than or is it less than or equal to? Is it equal to or is it not equal to? Because this is going to tell us whether it's our null or not. I hope this makes sense, and feel free to reach out to me if you have any additional questions. Thank you.